I'm ready. Cool. Hi, hello. Achieving Pexcellence. So, a few words about myself. Background from Hamburg, where we started using GStreamer to make a product called Mobi. We got acquired by Cisco, and Mobi turned into a product called Cisco Jabber Video for Telepresence. Mouthful. You can still download that for free, actually, if you go to ciscojabbervideo.com or something like that. Worth checking out. Basically, a video conferencing soft client. I said think manageable and standards-based Skype. Well, it used SIP and it used GStreamer for audio and video. We had a nice little echo canceller in there, H.264, H.363 support. And it's actually still being rolled out as we speak. Cisco has sort of decided it's end of life, but some companies have liked it so much that they're still rolling it out. And of course, I'm no longer Cisco, but I've heard it's still being, it's large numbers, hundreds of thousands. Then one slide about the company, Pexip. Was started by the former CTO of Hamburg. He basically envisioned a product where he wanted to do everything right. And he got a few guys. I was one of the lucky ones. And basically going in and disrupting, if you want, the idea of an MCU. So that's a multi-conferencing unit, a multi-point conferencing unit. And the idea is that with video conferencing equipment, you can call in, you can call in, you can call in, and we can have a meeting together, right? These things are terribly expensive as of today, so we wanted to disrupt on price. We thought we could do better quality. We thought we could do clever things in terms of geographical distribution. You could have, say, one server in Europe and one in Asia, and you could do clever stuff if everyone was in the same meeting. It's virtualized, so this is a software-only product, and it can run in your data center. So our first product, this was called Pexip Infinity, with a mouthful of virtualized and distributed video conferencing infrastructure. And we are only ex-Hamburg and Cisco people. Well, we're all ex-Hamburgers, and then we sort of had a little stop through Cisco. And the application is using Python for everything application, and then we're using GStreamer for everything streaming. And I asked my colleague today to dump a pipeline in the ongoing "My Pipeline's Bigger Than Yours" challenge. It doesn't display really well, I think. See if we can try. It's not, yeah. Well, this is, what is this? This is, I think it's 40 people calling into the same conference using HD. Every single one of those 40 having their own instance of an RTP bin with corresponding mixers for audio, video, encoders, decoders. It doesn't display really well. Basically, this is an element, right? I think it's a few thousand of them. So it's big. So let me get back to that was definitely a sidetrack. Sorry. So what I wanted to talk about today is sort of through these years, which is for I'm started on my 7th year as a GStreamer developer, in a way. And we've encountered a lot of problems, as you would expect. And maybe one of the main ones, if I could categorize it into two categories, I would say one being that it's more than one thread, which is always a problem. Because once you have two threads interacting, you can have all sorts of funny race conditions. which could lead to unexpected behavior, my favorite being the deadlock. I've had call stacks from customers debugging deadlocks that involved 7 threads, like first this one, and then that waits on that one, waits on that one. And finally it gets back to, okay. And then, of course, crashes. The other problem with like live streaming, if you want, is that you can even think philosophically about it. I mean, Edward before talked about time. You could say that 1 buffer or 2 buffers will never hit your product in the same way, ever. And that is a problem, right? Because everything is so friggin' live that you have to account for so many different things. And it makes it hard to grasp, anyway. And my classic example being the audio problem, right? Because with video at 30 frames per second, you can easily lose a few and you will never notice. With audio, you lose 1 of 10 millisecond packets out of 100 per second, and it can be very audible. Or if it comes a bit late. Yeah, you get it. So, how do we solve these problems? I've basically wanted to, my message here today is that it's actually very simple. And this is how I propose to solve all problems with GStreamer. And I also sort of wanted to add in there the even more powerful solution where you have a continuous integration system running together with this. This next slide was meant to be preaching tests to all of you and saying, rah! But I already today, both the 2 imps, both Wim and Tim, have said that tests are something that we're wanting to do and lacking and more QA and stuff. So I feel like, ooh, that fits well. That's exactly what I'm going to say. In my experience, and it's been an experience that's, for me, it's been very interesting, because when I started developing GStreamer, I didn't write a single test. I mean, if you're good enough, you don't need to write tests, right? But for me, it's been a 7-year experience where it's almost a weekly thing. For every week that's been going by, I find it more and more important, just from pure experience. So now I'm somewhere between fanatic and lunatic, but I'll try and tone it down for you guys. So basically what I want to do today is to present you with, it's a sort of a little framework, tiny framework that we've written, that we are actually now using for all our testing for GStreamer. And yeah, we have a lot to get through, so we better get started. GStCheck. It is a great framework. You can easily write tests. You can easily run tests. It's easy to debug tests. You can test your tests. This is something we do quite a lot, actually. If your test is stable, it should pass, 1 million runs, right? Valgo integration is someone that I've come to really, really value. And GStCheck, as it is today, both in 0.10 and 1.0, has sort of something that I would say is the beginnings of something, an ID that's been used a tiny bit throughout GStreamer. And what we want to do is that we sort of, okay, this is a good ID. How can we extend upon this? So the imaginative name of GST harness was born. It basically does what GStCheck set of element does with extra stuff, if anyone's familiar with that. And the evolution of GST harness has basically been that whenever we needed something new to test in terms of GStreamer elements code, we have tried to use the GST harness for that, and hence it has needed to go through a lot of evolution, if you want. We have to, okay, we we need to be able to test and see if we received an upstream event. Okay, so then we need to add stuff to test that. And okay, we need to be able to test deterministically the jitter buffer. Okay, then we need to add some stuff to that. I think last time I looked in our sort of make, if we write make check and hit enter, it'll run roughly 600 tests for us currently. And almost every single one of them uses this GST harness now. And the goal for us with this was, of course, it should be super easy to write simple tests and easy to test complex scenarios, which is very important. So let's have a look at how it looks like from the very basic. You have your element. So the GST harness, this is exactly the same as check setup element does. Basically creates two floating pads, one source pad and one sink pad, and hooks them up. So now you could almost think of it like that element, in a way, now thinks it is in a real pipeline. For all it knows, it's running normally in a pipeline. Little does it know that it's in fact it's being probed and prodded. But for that little element, it sort of it thinks everything's okay. So now, super basic usage. We want to push a buffer through our element, right? So we have this function called GST harness push, which will take the buffer, push it onto the source pad. So the element will now receive that buffer on its sink pad. It'll do whatever magic the element does. It'll hopefully give us a buffer on the source pad. And then we can pull it. So, enough talking. Let's write a test. So the question is, does GST identity modify buffers? Anyone know the answer? Let's see. If I can manage this now. Here's a little something I prepared earlier. Okay. Come on. Okay, I'm going to take the whole thing. Let's quickly look at this little file. What is this? This is what my test is going to look like. Basically, there's a few aliens here, right? Pexcellence test.h, that's obviously proprietary. We use Pex as our namespace, of course. The only thing that does is that it contains this macro, which is a complete ripoff of GST check main, which sets up the pipeline. However, we do plugin loading. We have written quite a few proprietary plugins, and we need to load them before running the test. So that's all that's going on there, I promise, is that it loads a few plugins and then calls GST check main. Then we have GST check header, and of course, the topic of today, GST harness. And this is what your typical test suite code would look like. Notice that you can create different these test cases. I call my GST conference demo. It actually ends there. So let's paste in our test and have a look. Conference notes in the test. Here it is. Conference demo, push and pull. Let's talk through this quickly. We make a harness. We're putting the identity element. I'm going to just create a buffer, new. I'm going to push that buffer into the harness. I'm going to pull that buffer out of the harness. And I'm going to assume that identity actually changes the buffer pointer. So I'm going to say, OK, in buffer must probably be different to output. And I'm going to tear down the harness, test finished. Let's run that thing. So this is the only test I have here now, but confdemo.check should then run that test if I remember to add this here. My first test case. Beautiful. Whoa! They're not the same. Or they are the same. What do you know? So that must mean GST identity does in fact not touch the buffer pointer at all. Let's try that again then. Okay. Fantastic. So we now proven for once and for all that GST identity does not in fact touch the buffer. That's good. At least not then. Moving on. How about if I... No, do this. Yeah. How about if I tested the queue instead? That was a lot of stuff to go back and forth. Okay, let me show you here. I'm basically now going to replace the identity element with a queue. You all know the queue. And I assume now everything will be sweet, so let me just run that test. Huh? What happened here? Can anyone tell me why this is failing? Quick question. Any suggestions? It worked with identity, right? So why did those? Yes. You get a brownie. The right answer is because there is another thread. Because the queue introduces another thread, so our test is basically racy. Ugh. Let me prove that to you by adding a use sleep of a second. Because that's the way you do it, right? Per sec, like that. I'm now going to sleep for a second, and just going to sit around for a second and wait. Ooh. I'm probably better off sleeping before I pull the buffer, right? Woohoo! Passing test. Of course, this is unacceptable because we can't be using sleep people, right? So what do we do? I actually started from the start, sorry. Yes. Here's the problem. In beautiful graphic, that's a thread. Push the buffer, it goes into a queue, and just as the buffer is coming out of the source, it really is on the way, I already have pulled the thing and it's too late. Right? How do you solve that? It's a perfect solution, and it's called the GAsync queue. Basically, if you notice the API here, I was using the try pull, which basically does a GAsync queue try pop, which means it's going to go to the async queue and say, I'm going to grab whatever is there, and there was nothing there. However, the GAsync queue timeout pop is going to go to the queue and say, whenever you have something within this timeout, we use a large one, 60 seconds, whenever you have something, I'll have that, please, right? So, by doing that, the test will, basically, if you can think that in the sync pad of the harness, we have a queue. So we implement chain method on that sync pad, and in the chain method, all we do is pop that buffer into this queue. Now this is incredibly powerful because it means that the test will now, if we use the new API, let's try that, the test will finish just the right time. Because once there is a buffer available, this pull function will get the buffer and it should work. Let's try it. Din, 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 din. The sleep is removed. Yes. This is the magic word. So, I can't really stress this enough because there is a really important lesson here. It talks about, we have, like, what it sort of, for me, it paints a picture of being able to write deterministic tests in for a very multi-threaded environment. And I'm going to show you how this can be used further. This was basically what we did, right? We push the buffer in, the buffer goes into the asynchronous queue, and then we can pull it, and the pull will wait till there is something there, and then we get it. So now we have a completely deterministic test that actually is sort of multi-threaded in its core. Now, let's step it up. Let's try and test a source element. Okay. I'm then going to have to copy this stuff here. We'll make a new one. And let's have a quick look at what this test does. Audio test source, well known to all of you. I'm going to create it. I'm going to set it to be live. I'll talk a bit more about that later. I'm going to start it. This is different from the previous test, did you notice? Because here we didn't say play. The reason for that being that the harness actually detects that this is a source, and hence it knows that if I put this to playing immediately, I'm going to start producing a lot of buffer. Now that's not very deterministic, is it? So for source, it actually, for this test up here, as part of this harness new, it will actually put the cue into playing. Whereas here, it doesn't. We're going to try and pull a buffer out of the test source, and we're going to verify that we have only pulled one buffer out of it. Okay? Let's try that. Just to check that we can, you know, completely control the test source. Nothing fishy going on. Okay. Here we are. Now, a little neat trick with check. If this is the only test I want to run, GST checks equals that one. Make const demo.check. Okay. Let's see. It worked. Great. Shall we try it again? Ooh! What just happened? Are you telling me we're having another racy test? Can someone tell me why I suddenly received 2 buffers here instead of just 1 in the first one? Okay, I'll tell you. It's racy. And I'll show you why it's racy. Okay. Behold, audio test source. We've set is live to true. That means that it's going to go to the clock. There's been a lot of talk about clocks today, so you should be fully knowledgeable about those. And it's going to say that for time 0, say if it's outputting 100 buffers per second, it's going to say for time 0, I'm going to output a buffer. For time 10 milliseconds, I'm going to output another buffer. Now what went on in our test, the reason it failed was that it had time to produce 2 buffers by the time we called this function. So from we said play on the source, it just started. It starts up and it produces buffers. So, but this is not acceptable, right? We want control. So, what do we need? A way to control time. And the name is GST test clock. It's a GST clock implementation. It allows you to control the time any way you like. It does not advance by itself. You have to advance it manually. It allows you also have to release the GST clock ID weights manually. And it's already in GStreamer 1.0. You can go and find it. It's awesome. So, how can we do this? Basically, once you've set a isLive property on a source, it means that for every single buffer, it's going to go look at the timestamp and say, whenever I'm going to register a clock ID weight for that, and when the clock reaches that, I'm going to push it. So if we replace the clock with the GST test clock, it means the source will be waiting for us to take action. And the GST test clock is a bit tricky, so we've simplified it a bit, because everything is sort of extremely manual. So we have managed a concept that we call a crank. So a crank is pretty much the only way we use the test clock. I mean, It's possible to use it for really detailed things like, okay, I'm going to turn the clock a tiny bit more, I'm going to verify the buffer timestamp, I'm going to twist it a bit more, and I'm going to increase it with a nanosecond and see if that changes something in decoder, etc., etc. For most purposes, it's the releasing of the clock ID weights that we are using it for, because it allows, again, determinism. We can freeze time and control it. So a crank consists of four points. Thank you. It waits for the given number of weights, so you can say you can wait for 2 weights or 3 weights, but in this case we're going to wait for 1 weight. So the clock is going to stand there and wait until it gets a weight. Yeah, you get it. Then it's going to look at that weight, because that's going to be registered with the time, and it's going to say what is the lowest, or the lowest is obviously for more weights, but it's going to, nevertheless, here it's going to look at the time. What time is he waiting for? And in the audio test source, it will be, it'll start waiting for 0, and then it'll wait for 10 milliseconds. Then it's going to go and advance the test clock to that time, and finally it's going to release the weights. So you basically have said crank for the time. So then it looks like this, in a way. There's a GST harness. The harness sort of builds the test clock into it, right? So there's a GST harness crank single clock weight. So what that basically does, it's now going to go to the test clock and say, whatever weight, when you get a weight, and this is important, when you get your first weight, hold that and then crank it. And then it'll release that as a buffer to us, and it'll go and wait on the next one. So in the test, this means we need to do a few things. I'm going to copy. Because I can't be bothered writing. Sorry about that. And what we added here is this one, GST harness use test clock. So now we're telling whatever elements we've harnessed up that basically it's a GST element set clock, right? You take the clock and you go, this is what you're going to use now. And then we're going to crank once, and then we're going to verify that we get 1 buffer. So let's run that test again now. Bam. But you saw it failed before, right? So let's do forever, just to... they're all passing. It's actually flying by here. It just looks like they still. So, again, another super important concept I want to stress a lot. In the name of determinism and testing, this allows us to control time, and hence to make a deterministic test for the GST audio test source. Now, of course, I could take that buffer and I could inspect it, and I could look at it, I could see what's the timestamp, what's the samples it contains, are they of this particular sort. But most important is that this test now behaves the same every single time it's run. There's no raciness. We've taken out the raciness of it. A new concept, sub-harnessing. We quickly found that only having, once you wanted to do a bit more than just testing a single element, we needed more context, we needed more stuff. And again, it's in the name of determinism. If you could imagine that you're going to test a long pipeline, and there's going to be several context switches, like maybe 3 queues and a few clock ID weights along that huge beast. Now, if you don't really care what's going on in between, it's fine to be deterministic at the end. You could just say, okay, I'm going to pull the buffer at the end, and cool, I got it. However, if you need to sort of piece it up a bit, say that you want this part of the pipeline to produce 1 buffer. Say, for instance, let's do the video example. You have a video encoder. You want it to produce, say, for instance, the first iframe. You push an image into it, and it's going to produce 20 buffers, 20 pieces of iframe. And that's all going to go into your decoder, who's going to decode all that into 1 frame again. Maybe you want to make sure that in between there, you actually got 20 buffers. You want to assert that I got 20, not 19. Or you want to inspect them and check that the first one was an SPS and the second one was a PPS, etc. So, let me show you how that looks. It's almost like you can basically have another harness on the harness. So if this in blue is our standard harness, I've added a sub-harness with a source. This means, and then we made a utility function that's called GStHarness push from source, which basically means that it's going to do three things. It's going to go and crank the clock, so as to release the buffer if it's waiting on the clock. It's then going to pull the buffer from there into sort of here, and then it's going to push that buffer into there. So you sort of have a deterministic mechanism to produce buffers, which you could use to feed anything. You could use it to generate any sort of data that you want to test within your element, and then push it in. Now, let me show you how this can work. I'm going to quickly, I call this the source harness. Let's quickly look at this. It sets up a harness for a queue, and then it's going to do a GStHarness add source. Basically what this then does is to create a sub-harness using the audio test source. It's going to set it to live again, so that it'll sync on the clock. And then it's going to do a push from source, which is going to do all those things. It's going to crank the audio test source, it's going to pull the buffer it produced out of it, and it's going to push that into our queue. And then we can pull, which is now from the other side of the queue, and see if that buffer made it all the way through, right? It's fairly simple. So a quick just demo of verifying that the source harness works. Make conf demo.check, and it does. I should have made it assert otherwise. Okay. Play from current slide here. Now, I want to combine all these things that we talked about before into a slightly more complex beast. And the test I'm going to write or show you is basically this. I want to write a test that verifies that an H.264 decoder will send a key unit request when there is packet loss on your network. It sounds fairly complex, I hope, or else this is not working. But let's have a quick look at that test. And I want to do this in 2 steps, just to make sure you can follow. Let's see. I'm gonna take this one out. Sorry. This is where we want to end up. Okay, so have a quick look at this one. H.264 decoder key unit on packet loss. So, first of all, this shouldn't come as a big surprise. Of course, GST parse launch is awesome. It creates a bin of any element. So basically, we just wrap that, and instead of testing the single element, we can also, of course, test a bin, which is, for all purposes, actually also an element, right? So I'm now going to set up the harness itself is going to consist of the jitter buffer, an H.264 depayloader, and our in-house H.264 decoder. Now, as the source harness, I'm going to set up a video test source, caps. Notice that this is 010, a caps for 720p, an H.264 encoder, and a H.264 payloader. So, my source harness can now give me RTP payloaded H.264 packets, right? Fairly simple. I'm going to tell the video test source to be live, and I'm going to use, I think 3 is white. The reason for that is because I like white. No, whatever. I'm going to play the source harness. I'm going to do the crank and push many. So it takes two arguments. First argument is how many cranks, and second argument is how many pushes. And here you have to understand that one crank will have video test source produce one image, which is going to result in our encoder, given the default bitrate and the resolution, is going to produce 5 packets of the iframe in this case. So these 5 packets are now being pushed from the source harness as the producer into the main harness, which basically means it first will go into the jitter buffer, then the depayloader, and then the H.264 decoder. Now, it's important that you can grasp that a pull now, if I actually get an output buffer, it means our decoder has decoded something, which probably means that all the packets made it through. Let me demonstrate. So I have now, I'm going to add this test. Is it the right one? I hope so. No. Yes? No, I was wrong. Sorry. Here. I'm going to GST checks it. Conf demo.check. So the fact that this is now passing means that we produced an image, we encoded it, we payloaded it, we jitter buffered it, we depayloaded it, we decoded it, and it gave us a thing in the end. To prove the point, let's try and only give it 4 of those 5 bits of iframe, right? And now the test will be standing for 60 seconds waiting for that poor buffer to pull, and then a little timeout. So, no luck. So obviously, it works. I'm going to go to the next version of this guy now, where we actually now add in the last bits. I've even added some comments. Push the first frame, and yes, we verify that it got decoded. Notice since I'm not interested in the buffer, I'm just unreffing it directly. So this is how far we got in our first example. However, now I'm going to crank 2 more times. So I'm now producing 2 more images from the video test source. However, notice that there's no pushes. This means that our frames are now going to be living in between the harnesses as they were. They're going to be living in the source harness's ThinkPad queue. And then I'm going to be evil. I'm going to go into the source harness, pull out one of these 2, and unref it. Which basically means that now it's going to make, there's no surprise, it's going to make 1 RTP packet per image, because it's had the initial iframe, and now it's 2 p frames, right? So this has been payloaded, so there's a sequence number on these ones. So I'm now going in, the 2 buffers, I'm taking the first one, dropping it on the floor. Now the second one is being pushed. And notice I can use this crank and push many again, where I'm not going to crank again, but I'm just going to take that other buffer and push it in through the jitter buffer. Does anyone know what the jitter buffer does when it sees a discontinuity in sequence numbers? The correct answer is it's going to start waiting for that missing packet. And that wait uses a clock ID wait on the clock. So if I now go and say crank, it's actually going to go and find that wait, and it's going to release it, which means for the jitter buffer, it's that, oh, that packet never arrived, I have to do something. So it's going to stop waiting, and then in a similar fashion to how we did buffers, of course there are pull mechanisms for events, queries, these kind of things as well, and we're going to go pull an upstream event, and we're going to verify that this event has the name GSD force key unit, which means that in however magic fashion, I don't need to go into that, but it means that once the jitter buffer saw a discontinuity, the decoder is somehow going to now respond with asking for an intra. Make sense? And I'll run this test. And it passed. Woohoo! Which means we now have a deterministic test for the fact that our H.264 decoder will produce a key unit event on packet loss on the network. It's a good stuff, right? And that sort of concludes my deterministic testing section, because I want to now quickly talk about a complete opposite, which is stress testing. Stress testing is basically also built into the harness in a way, but it's fundamentally completely different. It tries to bombard every single aspect of what there is to be done with streaming as fast as possible. It's extremely random, and we found that this can uncover a lot of rare crashes for us. It's even so that if we really stress an element, when we use this with our CI, we've sometimes found that the same test can be running, say, 100 times per day, and once every 2 weeks it'll fail. And that tells us there's something racy going on, because the race might be so impossible to catch that it'll only show its head once in a while. But we find, again, the power of CI, that we suddenly have a visibility for a once in a billion crash. I tried to make this slide to show you some of the stuff that we sort of built into the harness again. Some of these are, of course, not relevant anymore, but you can request and release pads, push buffers and events, again, as fast as possible. Do the same thing there, event queries, set the element to null and playing, back and forth. I'm going to skip this one and jump to this. Because as last thing, I wanted to show you a stress test for a funnel. Now, let's see how it looks quickly. TSD checks, funnel, make, check. Okay. Sorry. Before running it, let's have a quick look at how it looks. I'm creating a harness for the funnel, and I'm creating another harness also for the funnel. This is this slide I skipped quickly, but basically talks about how harnesses should be thought about per pad and not necessarily per element. So basically harnessing up 2 of the sync pads, because you all know the funnel, lots of sync pads, 1 source pad, first in, first out. I'm going to make a buffer, and here comes these stress functions. So by now it's harnessed up, and I can now call GST harness stress state change start. I can stress push single buffer, and I can stress request pad, which means it's going to release request pads as quickly as possible, push buffers as quickly as possible, and set the whole element to null and playing as quickly as possible. Going to do the same for the other pad, and here I have a sleep. This is interesting because these things are going to go for as long as you like. So basically what you're defining here is how long do you want the test to go for. I've said 1 second. Because we're slightly superstitious, let's say 3. I'm going to stop all the stressing. I'm going to unref the buffer, tear down the harness. You get it. Now, let's try it. Conf demo.check. What am I doing wrong? Make, thank you. 1, 2, 3. It worked. Good stuff. What I'm doing now is reverting a patch that we have on GST funnel. Boo. Okay, let's run the test again. 1, 2, 3. 4, 5. I think we have deadlocked people. Let's use GDB and find out. Oh, come on. 1, 2, 3, 4. Surely it's deadlocked by now. Okay. Thread apply all backtrace. You all know this stuff. Huh. Look at thread 5 here. In GST funnel change state, it doesn't make really sense that it should be. Why is it not finished with this stuff? It's sort of standing. It's almost like it's standing still at GST funnel change state. You can see it's doing something with an iterator, but surely this should be finished by now, right? We've ended the test. We've stopped it. So it must be doing something. Big disclaimer, this is 0.10 code, but it is what is in 0.10 right now. And let me first... Sorry. Oh, sorry, I've completely forgot. Let's look at the call stack. We were in change state. That's GST funnel line 502. Okay, so let's jump to line 502. Ooh, can anyone spot the mistake? It's 10 points to spot the mistake. What happens if you get the GST iterator resync? What do you have to do? Can someone tell me? Come on, guys. You have to resync the iterator, right? So basically, if you don't do if res equals this, I'm a copy-paste programmer, then if you don't do that, it'll be, huh? Iterator. Thank you. GST iterator resync. If you don't do that, this loop will just go on forever, because it'll keep returning resync, and as long as you don't resync it, it'll just keep going. And we'll run this, we'll compile it, and I'll quit this, see if it's compiled. Sure, we're going to run our test again now. Run. 1, 2, 3, passed. So, it basically found a deadlock that's been in funnel since the beginning of funnel days in 3 seconds. So, and my big disclaimer is that this bug is fixed in 1.0, so not to worry. It is completely fixed. I know I'm pushing it for time here now. I just want to say, in terms of improvements, this GST harness is definitely going into GStreamer. We have finished porting it to 1.0. It still has a few PEX specifics in it. We need to make it a bit nicer, you know, the whole thing before it goes upstream. We are going to move all the tests that we are doing currently in our framework into the GStreamer framework for testing GStreamer elements, and hope to keep evolving it with use cases. And we hope to have it to all of you before Christmas. And I want one word about the GStreamer element acceptance test. It's very easy to imagine that once you have something very complete in terms of this harness that can do all this stuff, you could basically just do GST harness acceptance and go bang, and it'll do the queries, the probes, it'll check the buffers, it'll do the pushes, and it'll basically tell you if you have a decent GStreamer element on your hands. Could be great for sort of people writing new elements. Thank you.
I don't know if we have time for questions. Maybe one question, and then otherwise coffee gets cold. Better
be a good one.
Yeah, it's a good one. This promise to deliver by Christmas, is that with documentation and examples?
It'll be with tests, which are your best documentation.
And which Christmas?